So we'll take a quick look at the calendar. Today we're going to talk about quadratic models, that is word problems. Notice that there is no class on Monday, which is Patriots Day. So I pulled up the academic calendar. This is Monday. No day classes, but if you do have a Monday night class, you should go to it on Monday. And the Wednesday coming up is a special day. It won't affect us, but Wednesday follows a Monday schedule during the day. So you treat Wednesday during the day like it's a Monday. Any questions on the calendar? Okay, and on that Wednesday, which is like a Monday, we have our fourth quest. And again, the quest is on classes 24 to 30, which is all the stuff up to but not including today. All right, so the stuff we do today with word problems is not on the quest. All right, so let's jump in here on, yes. Yeah, our final is on Monday the 19th, 8 to 10 a.m. Yeah, the schedules were actually, they were known before the semester started. They were just sent out recently, like as a reminder, but I looked it up before I printed this. Yeah, this is correct. All right. Okay, so again, we'll jump in here on page 62. Let's start up here at the top. So it says work with your table mates. Let's just do this together. So this activity has to do with the height of a baseball. I'll go to Alex for this the formula part.
Formula for the height of a baseball starting from the air -16 feet squared plus 64 feet plus 4, where h is the baseball's height and t is
Okay, so let's see if we can do number one together, which will make sense of that formula that we haven't seen before. One says complete the table of values for the height of the baseball. So for example, if we take t equals 0 and substitute it into that formula, t equals 0 into that formula, both things with t's in them zero out, they disappear. All that's left is a 4, which means that 0 seconds into the flight of this baseball, it is 4 feet off the ground. Basically means you're throwing it from a height of 4 feet off the ground. And then it's going to go up and then slow down and then stop for just a moment and then come back down and hit the ground. So let's see what happens if we plug t equals 1 into that same formula. So -16 times 1 squared plus 64 times 1 plus 4. So we need to know what this is. Everybody see what we're doing? Substituting in 1 for those t's. So 1 squared is 1 times -16 is just -16 plus 64 plus 4. So what do we get there? Is that 52? Is that okay? Okay, now I want to save a little bit of time here as we fill in the rest of this table. So I'm going to do a little shortcut, but is everybody okay with the process of filling in the table, even though we're just going to do it on the calculator real quick? Any questions on what we did over there? Okay, so if you have one of these calculators, you're welcome to try this later on. You can check out the video if you want to see any of the commands, but I hit this y equals button. I typed that formula in -16. There's no t on this one, it's an x. X squared plus 64x plus 4. And then I do second, and then you can't see it, but the word table is this top right one right above the word graph. And right there it says if x is 0, you get 4, which is exactly what we said. And if x is 1, you get 52, which is what we said. And now we're just going to fill in these other numbers. So it's just a little shortcut. So we get 68, 52, and 4. Okay, so what does that mean? Well, t equals 1 represents 1 what? 1 what? It is the input, but what is it? It's 1 second. And 52 is 52 what? Yeah, it's the height, which is measured in feet. That's what it says up here, right? So 1 second after you release this baseball, it's 52 feet off the ground. 2 seconds after you release the baseball, it's 68 feet off the ground. 3 seconds, it's back at 52, which means what happened to the baseball? It's on its way back down, right? Okay, so what I'd like you guys to do is plot those 5 points over here on these axes. And once you've got 5 points plotted, you're going to connect them with a smooth curve. What's the name of the curve we just drew? Parabola. And we shouldn't be surprised as a parabola because parabolas come when you're graphing x squared, y equals x squared. That's what we're graphing. It's just a t instead of an x. Are we surprised it opens downward? What in that equation says that we knew it was going to open down? Negative for a, right? But negative 16 says definitely opens down. Great. Number 3 says write in the coordinates of the highest point. 2 numbers. What are the coordinates of the highest point? 268. You guys 100% sure that's the highest point? It's the highest point we were given. Does that make it the highest point? Not necessarily. Couldn't it be a little bit higher if we were looking like 2.1 seconds into this? Like maybe it was still on its way up. Yeah, so Alan's right. I mean, it definitely is the highest point because we've got this kind of symmetry. Like at 1 and 3, we were at 52. We were at the same height 1 second and 3 seconds in. And so anytime you got 2 points that are at the same height, that top point is definitely halfway in between. So yes, it is definitely the max. But I just wanted to point out, like just because it's the biggest number in the table doesn't mean it's the biggest number on the graph. Okay, so let's fill in here. The baseball reaches, there's a typo, reaches its maximum height at how many seconds? 2 seconds. The maximum height of the baseball is 68 feet. Okay, we're going to skip number 4 and 5 and jump down to number 6. It says use your graph to find 2 times when the baseball's at a height of 64 feet. 2 times when the baseball's at a height of 64. So, height of 64, where are we going? To the horizontal axis or the vertical axis? We're going to the vertical axis. So we'll go up there at 64. Just going to have to estimate 64. And then what do we do? We're trying to find the other coordinate, the t. So where are we going on the x-axis? So I need to draw something. What are you saying I should draw? Okay, so we draw a line. Horizontal line. Okay, so let's draw a horizontal line. And we find 2 different points where that horizontal line hits the parabola, and those are the 2 winners. And so from each of these 2 points, where do we go? We go straight down to figure out what magic t value we landed on. Now your t's are going to be a little bit different than my t's. For me, I get something like 1.6 and 2.6, but it's just an estimate. free to write down different numbers for those. Whatever your graph says is what you should write. And so those are my answers to this question down here, number 6. It says, when is the baseball at a height of 64 feet? Baseball will reach a height of 64 feet at t equals 1.6 seconds and t equals 2.6. Again, you can put your own numbers in there. Any questions so far? We're going to skip 7. It's the same as 6. But what I'd like to do is figure out how close we were to the right answers on number 6. I said 1.6 and 2.6. You probably said different numbers. I want to know how accurate we were. We were estimating stuff from the graph. So here's what we can do. Go back to my calculator. I find it really funny that the calculator, which is emulating the actual calculator, goes into power save mode after a couple of minutes of inactivity. But it's a virtual calculator. There's no batteries that are being drained. Anyway, one thing that I can do if I want to figure out what's going on at some particular numbers is I can change one of these settings in here. And then it's just waiting for me to tell it what x is. So for example, if x is 2, we're still getting the 68 that we got before, right? 2 and 68 were in the table. But now I can type in 1.6 and it will tell me what the answer is. What am I hoping the answer is close to? Yeah, we're hoping it's 64 because that's what we were shooting for. Okay, that's not bad. What am I hoping for 2.6? Also 64. Okay, that's a little bit worse. But these are where the ball is after 1.6 and 2.6 seconds. Okay, so we can see that just looking at the graph has some weakness involved, right? Because we're estimating. So let's do this the better way, the algebraic way. I'll write down some answers over here from the calculator. The ball is actually at a height of 65.44. It's not bad. We were hoping to get close to 64, and we did, but it's not perfect. So let's do this the algebra way instead. I want the height to be 64. So looking at this equation in number 8, the one in parentheses, which variable are we changing to a 64? It's the h, right? It's not the t. We're trying to find the time, but it's the h that becomes 64. So I'm just going to rewrite that equation, put a 64 over here for the h. Everything else copied. Be careful that your t's don't look like plus signs. And now I'm not thinking about the graph at all, but just looking at this guy, that's a quadratic equation. And we have lots of different ways to solve quadratic equations. Generally, the first step is to do what? Before we factor, 0 on one side, right? 0 and then factor was our first attempt. So let's make a 0 on one side. Do you want to bring everything to the right or everything to the left? There's no wrong answer, but I'm just looking for your impressions and why. So why do you want to bring things to the right, Alan? It's only one thing to move. That's reasonable. Boo, why do you want to bring things to the left? Which negative? Yeah, we could make that t squared number in the front positive by moving things to the left. These are both compelling reasons to make different choices. I just want you to be thinking about like why you're moving things where. If the ultimate goal is factoring, then I would prefer Boo's suggestion to make it a positive in front of the t squared. But if we're going to use the quadratic formula, then Alan's got the easier way by just moving one term over. Let's move everything to the left and see what happens. So we're going to take that negative 16t squared, add it to both sides, becomes positive. This plus 64t, what do we do to move it? Subtract it. This plus 4, we're going to subtract it. What's going to happen when I subtract the 4 from the left side? We'll get plus 16. Okay, before we think about quadratic formula or maybe the like 2 parentheses kind of factoring, there's another kind of factoring that you should always look for first. What number goes into all 3 of those numbers? 8? 4? Which one is it? I think 4 goes into all of these. 8 goes into the first 2, but 8 doesn't go into 60. So I think 4 is the best that we can do. So we're going to pull that 4 outside. It doesn't just disappear, just moves to the front. So this 4 is going to distribute into whatever we put and better end up giving us exactly what we had. So 4 times what is supposed to give us this 16t squared? 4t squared is right. Because then when we multiply here, we get 16t squared minus, now we got 4 times something is supposed to give you that 64t. So 4 times what gives 64? 16. And then we also need the t. That's a 16t. And then the last piece, 4 times something is supposed to give me that 60. 15 is good. Plus 15 is there. Okay, so now we have a choice to make. Do we try to factor this thing in the parentheses into something like 2 parentheses, or do we just bail out and immediately head to the quadratic formula? Again, it's something that like both options have merit. If it factors, then maybe we'll get there faster. Like if we can factor it quickly, then it's probably faster than the quadratic formula. But if it doesn't factor, then you have to go to the quadratic formula anyway, and you've spent time factoring something that had no chance. So one option you might consider is something that we looked at last class. You guys remember the discriminant? What's the formula for the discriminant? A squared minus 4ac. So we can do this calculation, and if we end up going the quadratic formula route, then we'll have to do this calculation anyway, so it's not like wasted effort. But this calculation can actually tell you whether or not you should spend any time trying to factor it. Let's give it a shot. B squared, negative 16 squared, minus 4 times A times C, 4, 15. Okay, negative 16 squared, you might not know, but it is yellow, so you can just look. 256. All right, 4 times 15, that seems challenging, especially if you do it in the order you see it, but easier would be this. 4 times 15 is 60, and then times another 4 is not hard. 240. So altogether, this is equal to 16. Okay, so let's see if we remember stuff about the discriminant from last time. That 16 is going to tell you how many solutions you have to the equation and what kind of numbers they are. So the kind of numbers, the choices were rational, irrational, or complex. Which one is that? Irrational? Rational. Okay, so it's definitely one of those two because 16 is a positive number, right? Negative would be the complex solutions. Positive meant that you had to look for something else. All positive numbers don't lead to the same answer. What was the other thing we had to look at to decide which way it went, rational or irrational? To see if it was a perfect square. Is 16 a perfect square? Happens to be. Normally it wouldn't be, but this one happens to be. And that means when you take the square root of it, you're going to get some nice numbers. Nice numbers. Are those called rational or irrational? Those are the rational ones. So this one we're going to get two rational numbers. And if you're going to get rational numbers, then it actually means the original guy factored nicely into two sets of parentheses. The fact is, using the quadratic formula after you've done this is pretty quick, so I'm just going to go that route instead of factoring. But it might be good practice to just try factoring this thing in the parentheses later on. It does factor. Now that I see a 16, a perfect square here, I know definitely that thing factors. Is it the easy product sum or the harder box? Harder box because of the 4 in the front of the t squared. But let's just finish this one off with the quadratic formula. Quadratic formula, x. All right, so normally it's an x equals, but in this case it's a t equals. Without looking at your neighbor's papers or any other papers, see if you can write in the quadratic formula from memory. I got you started with a big fraction line. How much of this quadratic formula do we know? The discriminant will be inside of there. Okay, go ahead and check your answer on the board. Raise your hand if you got it perfect. Oh, you were plugging the numbers in. That's okay. All right, so it looks like more than half of us have this memorized. That's great. Don't need to have it memorized, but with a little bit of practice, it starts to become more familiar. So let's do the calculation here. So what are we doing? Negative b. So I'm going to highlight here. This is the stuff that we're grabbing the a, b, and c from. So negative b is really positive 16 plus or minus square root of. Now this b squared minus 4ac, we did it already. Don't do it again. What is it? It's 16. Right, you just grab it and throw it in there. You don't have to redo that calculation. We're going to take it from the stuff that's in the parentheses. Yeah, and factoring out that 4 made everything smaller, which makes all the quadratic formula calculations easier. So definitely if you can factor a number out, you should do that. Okay, and then on the bottom is a 2a. So what is that in this case? 8, 2a times 4. 16 plus or minus 4 over 8. Okay. Normally we'd stop, but in this case, we're just going to get two nice numbers if we rewrite that separately with the plus and the minus. So let's just copy them both. So 16, 4, and 8. 16, 4, and 8. So exactly the same thing in both, all the same numbers. What's the only difference between, for the space? It's 1 plus and 1 minus. So the first one is 20 over 8, which is 10, which is what, 5 over 2. 2.5. 12 over 8 is 3 over 2, 1.5. So if you remember way back, the beginning of this problem said, when is the ball at a height of, was it 64? Yeah, when is the ball at a height of 64 feet? So the exact answers are 1.5 seconds into his journey and 2.5 seconds. My estimates were 1.6 and 2.6. Close, not exactly right. This is how you can get it exactly right. Questions on that one? So why are we doing this problem here with the baseball? Well, because it's an application that has to do with quadratic equations, right? We ended up getting a quadratic equation out of this baseball example. And it turns out that anytime you have an object that is thrown into the air, a quadratic equation is hidden underneath the surface. So I will show you that quadratic equation. It's on the next page. We are going to go to number 11. Yes, Alan. Yes. The 4. No, you don't use the 4. Yeah, basically we're dividing both sides by 4. Yeah, from this spot right here. If you divide this side by 4, it cancels. And if you divide this side by 4, what do you get? Still 0, which is kind of the nice thing. If it's 0 over there, then any numbers in the front are irrelevant. Okay, let's look at number 11. It says if an object is thrown into the air from a height of h sub 0, so I'm saying sub because it's a little subscript down there. So that h sub 0, the notation, the 0 means that we're doing it initially, like at the initial height. So that 0 really represents time equals 0, which is like when we start the stopwatch. So if you throw an object into the air from a height of h sub 0 above the ground with an initial velocity of v sub 0, so the v is the velocity part and the 0 is saying it's the initial at the moment we start the clock, then its height, t seconds later, is given by this formula. H is the height of the object. And so here's the formula. 1/2 times g times t squared plus v sub 0 times t plus h sub 0, where g is the acceleration due to gravity. So I think this is the messiest formula we have seen this semester. If you end up taking a physics class at some point, you will see this formula. It comes out of physics. And the first observation I will make, what's the power on the t? What's the highest power? It's 2, which means this is called what kind of an equation? It's the quadratic equation. And so anytime you have something that you throw up and it comes down, that formula dictates exactly how high it will be depending on how long it's been since you threw it and what that initial velocity was. Okay, so acceleration due to gravity on Earth is this number. It's negative 32 feet per second squared. What that means is if I were to just take this rock and I drop it, meaning the initial height, initial velocity is going to be 0. So if I just drop it, then 1 second later, this thing will be moving at 32 feet per second. The negative indicates down towards the center of the Earth. Okay, so if I drop this thing and let it fall for a whole second, 1 second into its journey, it will be traveling at negative 32 feet per second. If it, now it's going to hit the ground before 1 second has elapsed, but if I were at the top of the building here and I dropped it, it would fall for longer. If I let it fall for 2 seconds, after 1 second, it's at 32 feet per second. After another second, it's at 64. After another second, it's 96. So it's every second, it goes 32 feet per second faster. That's what this feet per second means. Is there, Victor? Wind resistance does come into play, but it's so minor for the speeds that we're talking about that we use this simplified formula, which doesn't take wind resistance into account. It's a good question. Okay, so let's try let's try number 12. I'll go to Ryan for 12. Okay, so this is really just practice with using this brand new formula. It's complicated. So h equals 1/2 times g is a constant. It's always the same number on Earth. What is it? G. Yes, it's a magic number that has to do with gravity, and here on Earth is always the same number. What is it? It's negative 32. It's just always negative 32 when you were here on Earth. So that G we'd always replace with negative 32. P squared is just T squared. So we're copying. If I see the first three terms all copied down, plus. Then we get to this V sub 0. V sub 0, remember, represents initial velocity. It's given in this problem. What's the initial velocity of the tennis ball? 25. 25 feet per second, so that goes 25. And then right next to the V0 is another T, so we'll put a T there. Plus H sub 0. H sub 0 is the initial height of the ball, which is given in the problem. 8 feet. Makes sense. You got a tennis player swinging a racket. I could buy that the racket head could be 8 feet off the ground, like on a serve. And so the only thing I'll do is just do this multiplication right here. This guy really becomes negative 16, right? 1/2 times negative 32. Megan, oh, all right. Can we what? The 8 and the 16? No, because the negative 16 is tethered to that T squared and the 8 has nobody next to it. So this is it. We can't reduce any further. And that's the formula that tells you exactly how high the ball is going to be at any moment in time. It's given by that. You could answer similar questions to the baseball thing just using this formula. Do you see something that's the same in the baseball example as in this formula? Like, look at the baseball formula and tell me, I think the baseball one is at the top. It is quadratic. Yeah, the baseball formula is still at the top of this page. What's exactly the same between the baseball formula and the tennis ball formula? A negative 16 T squared. And in fact, it's always negative 16 T squared here on Earth because it's always 1/2 of gravity, which is always negative 32. And so they're all negative 16 T squared. The only things that change are the numbers in front of the T and the numbers sitting here at the end, which are just the initial velocity and initial height. If we were playing tennis on the moon, that negative 32 would change. Right? Gravity on the moon is not nearly as strong as it is here on Earth. And so maybe that negative 32, I don't know what it is. Maybe it's like negative 5 feet per second that it speeds up as it falls towards the center of the moon. Okay? All right, let's move on to the next page. We'll tackle 14 together. I'm going to go to Lauren. Okay, so I don't have a piece of cardboard, I have a piece of paper. So here's my piece of paper that's representing this guy. And what we're going to do is we're going to cut out 4-inch squares from each of the 4 corners of this guy right here, okay? All right, so it's not going to be 4 inches, it'll be a little bit less. But I'm going to cut out 4 squares, and then we're going to fold up, and you guys are going to see this box come alive before your very eyes. Okay, so this is what we get when we cut out roughly square things from each of the sides. What are you laughing at back there? And then what we're going to do is we're going to fold this guy up. So I'm going to fold it right there, exactly where I cut out one of my squares. I'm just going to, or 2 of my squares, I should say. I'm going to fold there, and on the opposite side, we're going to fold, and then we're going to rotate, and we're going to play the same game, make 2 more folds. And we get this. This reminds me of when I tried to make an ashtray for my mom back in like the middle school shop, and it looked terrible, just like this. Okay, so this right here is a box with no top, yes? So this is what we can make from a piece of paper. Cut out 4 squares, fold stuff up, and you get like a shoebox type thing, just open on the top. That's yours to keep. All right, so this box is supposed to hold 100 cubic inches, and we want to know how big a piece of cardboard we're going to start with. Would you guys buy that if I started with a bigger piece of paper, I'd have bigger space inside of this box? Smaller paper, smaller space inside. So of all the different papers we could start with, we want to find the one that magically has a volume of 100 cubic inches inside. That's the goal. So let's give this a shot. We need to come up with a variable someplace. If you're not sure where what your variable should be, you look at the very last sentence, which is typically what the question is ultimately asking. What do they want to know? Go even farther past that. The size of the original piece of cardboard. It says how big a piece of cardboard, another typo here, my goodness, is needed. How big a piece of cardboard is needed? Okay, what does that mean? Well, I guess it means that we're taking this square piece of cardboard and we're trying to figure out how long and how wide it's supposed to be, but it's square, so it's the same number. So it feels like that would be a really good thing to call x. Is that fair? X is going to be the length of one side of this piece of cardboard, but it's a square, so it's the same on the adjacent side. So we can write that. X equal the length of the side of the square in, and then we'll want units. Inches is the right units here. Both numbers in this problem are given in inches. Okay, so that's our variable. All right, and now that that 100 cubic inches, what geometrical characteristic are we talking about there? To say that the box is supposed to hold 100 cubic inches. What is that? It's the volume. Yeah? It doesn't say volume, but that's what we're talking about. We want 100 cubic inches of space inside of this box. So clearly the volume of the box is what we're after. So let's see if we can get a formula for the volume. And I'll put the word box here just to highlight. I'm not talking about the piece of cardboard anymore. It's already been folded up. So forget about this particular setup, but in general, what's the formula for the volume of a box? Say it again. Half base times height. That is a geometrical formula, but it isn't this one. Length times width times height, or depth is okay. So we'll do L times W times H. Length times width times height. That's the formula for a box. Okay, looking at the box in the picture, one of these guys is actually labeled. Which one is labeled in the box picture? Is the height. Height is 4 inches. Does that make sense? We cut out a square of 4 inches and then we folded it up. Do you guys see that 4 becomes the height on all sides? Okay, so this guy is equal to, so I don't know what the length is, we'll fill that in, and I don't know what the width is yet, but I definitely know the height is 4. Okay, but now we got to figure out what the length of this rectangle is. So the length, I'll mark in green here, we'll say is like this distance from here to here. That's the length of the rectangle. Okay, let's come back to this guy for a second. Suppose that the original piece of paper, I mean, this is probably like an 8.5 by 11, right? So let's call it 11 on the one long side here. So it's 11 inches to start with. Can you guys tell me how to figure out what the length of the box is, like after I cut? Yeah, we're going to subtract 8 because we cut out a 4-inch up here, we cut out a 4-inch down here, so we're going to subtract 8. So it's 11 minus 8. We don't need the number, but that's the calculation, right? It's whatever the original length was minus 8. But what did we call the original length? We called it x. So that means that the length of the box is whatever x is, subtract 8. By that, used to be x, cut out 4 on either end. x minus 8 is what's left over. How about the width, which I'll say is that guy? It's also x minus 8 because we started with a square. So the length is x minus 8, the width is x minus 8, height is 4. Okay. There's one thing we haven't used yet in the problem. 100. What is the 100? It's the volume. So then couldn't we just change the v on the left-hand side to 100? That's the volume that we're after. Okay, and so now after all that work, I've got one equation with one letter. I mean, it appears twice, but it's just one x. And in theory, we can solve this equation if we know what we're doing. So let's give this a shot. I'm going to foil or lobster claw or something over here. And we got to do this piece. Push those guys together. So what do we get for the first? X squared. Outers. Minus 8x. Inners. Minus 8x. Last. 64. And what do I still have to do on the right-hand side? Times it by the h, times it by the 4. Did I write this correctly? We need parentheses, right? Because all that stuff in the FOIL was one thing. Still gets multiplied by 4. Okay, continuing merrily along, 100 equals. So let's first clean up in here because we can combine these two guys. Minus 16x. Okay, what's the next step? That's the clever step. What's the normal next step? What could we do on the right-hand side? Yeah, couldn't we distribute that 4? Perfectly correct. But you don't have to. And Alan's got a shortcut for us. What do you want to do to both sides? Let's divide both sides by 4. Because it's going to make everything smaller. We don't have to distribute. And 100 is perfectly divisible by 4, so this is good. Divide both sides by 4. It's not wrong to distribute. And you will get the right answer at the end if you distribute. It's just going to be bigger numbers. Okay, there's a familiar looking quadratic equation. What do we need to do first? One side is 0, so let's subtract that 25. $39. If we're going to try to factor, is this the easy or the hard kind? Easy. So I said this the other day, I think. Most quadratics don't factor. If you just make up a quadratic equation, just make numbers up, put them in front of x squared and x and then the last number, there is a very small chance that the thing you just made up factors. But if it's an easy product sum thing, then I would spend 30 seconds trying to factor it just to see. Right? Quadratic formula is a long way to go, and oftentimes it's the only way to go, but if it factors, then that's a short way to go. So let's give it a shot. Good news is 39 doesn't have all that many factors. So we need the product to be 39, and we need the sum to be negative 16. There aren't many things that go into 39. Victor says negative 3 and negative 13. You guys see that that works? Negative 3 and negative 13 multiply to positive 39. and they add up to negative 16. And even if it's okay to not see that right away, but I mean, if you're trying to build 39, it's either 1 and 39 or 3 and 13. Nothing else goes in. And just adding those up, we say, oh, look, the bottom one adds up to 16. Make them both negative, as Victor says. And we'll put them in here. Minus 3, minus 13. Okay, so I think we are ready to finish this one. So either 0 equals the first parentheses, or 0 equals the second parentheses. How much is x in the first one? 3. And the second one, 13. In solving quadratic equations, you will almost always get 2 answers. So not surprised to see 2 answers. But both of these answers make sense in the scheme of this paper getting cut up and folded. Mariah, what's wrong? Yeah, okay, so Mariah, I think intuitively feels like there should only be one answer. And we said the bigger the paper, the bigger the box. So we can't have like 2 different sizes of paper giving us the same size box at the end. Okay, that's, yeah, look at the 3-inch answer. Remember, the first thing we were going to do was cut 4 inches out of each side, right? Well, we don't have 8 inches to cut from that smaller paper. So even though mathematically, if you plug x equals 3 into this equation with the 100, you plug x equals 3 in here, it's going to give you something that's true. X equals 3 works in that equation. It doesn't make any sense in the scheme of this problem. So we have to reject x equals 3, just too small. Does x equals 13 work? So if we subtract a 4 and subtract another 4, then how much is left? 5. So the length of the folded up thing would be 5. How about the width? Also 5. What was the height all the time? 4. Length times width times height. 5 times 5 times 4? 100. Works. Okay, so the group activity is here. There are 3 problems. Expect that each of them will take a while, right? You got to set up, introduce some variables, write some equations, and then solve. There's a lot of work for each of these 3. Give it a shot, raise a flag if I can help.